With the wave equation set up in the previous lecture, we are now ready to see how electromagnetic waves actually come into being. We are going to keep our discussion very simple and consider plane waves. That means, the amplitude is going to be same over a plane traveling in one direction. In particular, I am going to take a wave traveling in the x direction. So, I am going to motivate you by taking E in the y direction and B in the z direction. And show you that if they vary with time and space, they can sustain each other. So, let us say E is at x, and as you go a little farther out, E changes to E x plus delta x. E is in the y direction. Similarly, B is in the z direction. So, let us put z here, and as you go a little farther out, it changes to B z x plus delta x, and it also is changing with time. Now, I know from Faraday's law that curl of E is equal to minus dB dt. In particular, in this case, if I take a square like this or a rectangle like this, traveling or traversing it counterclockwise, as shown these by black arrows, I know that by Faraday's law I am going to have integral E dot dl is equal to minus d by dt of B dot ds, where ds is the area element. Now, since E is in only y direction, therefore, the horizontal lines in this do not contribute to the line integral. Let the width of this rectangle be delta y, and then I am going to get, by previous, whenever we proved the Stokes theorem, I am going to get E y at x times delta y in the negative direction from the left hand side black line, and on the right hand side I am going to get plus E y at x delta y plus partial E y partial x delta y on the right hand side line going up. This is the line integral, which is going to be equal to minus d by dt of B times delta x delta y. Now, I am going to put a partial derivative here, because now this thing is not under the integral sign anymore. Let us cancel a few terms. This cancels with this, and I end up getting this whole thing then gives me partial E y partial x is equal to minus partial B, which is in z direction, partial t, because these two terms also cancel. So, what we get from this is, what I am taking is x direction, y direction, z direction. We have taken E going this way and B going this way, wave traveling to the right. We will again see how it travels to the right, and I get partial E y over partial x is equal to minus partial E B z over partial t. That is one equation. Let us now apply the other equation, which gives me curl of B is equal to mu 0 epsilon 0 dE dt. Remember, this is coming from the displacement current. For this, I will take a rectangle in the x z plane here and traverse it counterclockwise. Again, remember, this is my x direction, this is my y direction, this is my z direction. This distance is delta x, this is going to be delta z. Now, Stokes theorem gives me B dot dl integration is equal to mu 0 epsilon 0 d by dt of E dot ds. B dot dl, like in the previous argument, is going to be B at x, and we are going again in the same direction as z. So, this is going to be delta z. The lines parallel to x axis do not contribute because B is perpendicular to that line, minus B of z at x plus delta x, which I can write as B x plus partial B z over partial x delta x multiplied by delta z, and this is going to be equal to mu 0 epsilon 0 d E dt, E is in y direction, let us write the magnitude, times delta s, which is delta x delta z. Again we are going to cancel terms, this term will cancel with this, delta x delta z cancels with this, and I end up getting the equation minus dBz dx is equal to mu 0 epsilon 0 dEy dt. So, the two equations that we obtained are for this Ey going in this direction Bz, we obtained our partial Ey partial x is equal to minus partial Bz partial t, that is one equation, and the other equation is partial Bz over partial x is equal to minus mu 0 epsilon 0 partial Ey partial t. Let us see what we can learn about these fields from these two equations. Now, from the equation dEy dx is equal to minus partial Bz partial t, we see if the wave is travelling, this should be equal to plus or minus 1 over v partial Ey partial t, where v is the speed of wave. And this immediately tells you that Bz should be equal to plus or minus E y over v. I know electromagnetic waves travel with speed c, so let us write this, or we denote it by c, E y over c. The plus sign is for the wave traveling to the left, and the minus sign is for the wave traveling to, and therefore, if the wave is traveling to the left, minus Bz would be equal to Ey over c, and therefore, if the wave is traveling to the left, B will be pointing in the negative z direction. On the other hand, if I have Bz equals Ey over c, the wave would be traveling to the right. What you can see is that E cross B gives me the direction of the wave. Let us see how we can combine these two waves, these two equations. So, the equations I have is partial Ey over partial x is equal to minus d Bz over dt, and partial Bz over partial x is equal to minus mu 0 epsilon 0 dEy by dt. If I take this first equation, differentiate it once more with respect to x, I get d2 Ey over dx square is equal to minus d by dt of d Bz by dx. I have switched x and t, which is equal to plus mu 0 epsilon 0 d2 Ey over dt square. Remember, this is the wave equation, with the speed 1 over c square being equal to mu 0 epsilon 0. So, what we have argued so far is that if I have two perpendicular fields E and B, which vary in both in time and space, then it is possible for them to propagate and sustain each other, and they propagate with a speed c, which is equal to 1 over the square root of mu 0 epsilon 0. In the next lecture, we will be obtaining this wave equation more rigorously, directly from Maxwell's equations.